degree from Cornell University. He worked a working career for Hewlett Packard. Currently, he is the radio astronomy program coordinator at the Little Thompson Observatory and has written the program called ezRA Astronomy. That program is running up in the Drake's Lounge. It's running on a Linux laptop computer over near the window that looks out toward Jansky antenna. If the screen is dark, just go ahead and move the mouse and the screen will come back up. I'll be there this evening if you want to play with ezRA and do some of the things that Ted is going to demonstrate online. Be glad to work with you on that. And there's about 9 months worth of preserved data over the last several months on that laptop. So we can go back to previous dates. You can see what was recorded and how ezRA processed it. So Ted has made this program freely available to anybody for download. I believe during this presentation, he will explain how to get it if you're interested. It's a perfect program to run with scope in a box, as well as bigger scopes. You can operate on professional instruments as well as home built. So without stealing his thunder on the details of this, here's Ted Cline.
Okay, with a mic turned on, that works a little bit better. Okay, good. Let's do this, do that. Make him go away. I think I'm sharing already. And what we want is something nice and big. Good morning, everybody. I have to live up to that now. ezRA is short for Easy Radio Astronomy, but I call it ezRA. ezRA is a set of free PC software tools to help explore radio astronomy. The open source Python programs run on Windows and Linux. First, I will describe an experimental antenna. Then I will give a fast tour of how ezRA can conveniently test this antenna system. I have a lot of slides, so hold on. I'm trying to develop an inexpensive antenna for folks starting to explore galactic hydrogen. I'm having some success with an antenna made from wire, half-inch PVC pipe, and zip ties. I call it the PZT antenna. The material cost is about $20 US. The straight elements come from bare household wiring, like for power in the walls of your house. I used number 14 American wire gauge solid copper wire. Each of them is held down in a small notch in the pipe by a zip tie through the pipe, secured by a second zip tie. The zip tie ends are then removed. The driven element is soldered to a SMA panel mount connector. Its sturdy trombone design comes from Kent Britton's cheap Yagi.pdf. It connects directly to the LNA via a male-to-male SMA adapter. I use inexpensive 75 ohm TV coax cable, so the RF signal needs to continue on through an SMA to F connector adapter. I trimmed a PVC pipe tee and strapped it to the boom with electrical tape. I poked the electronics and cable through a plastic sandwich bag and then assembled it through the PVC pipe. I strapped the electronics package to a short protruding pipe stuck in that pipe tee. I wrapped all that in a larger bag and then wrapped again in a reflective white shopping bag. Then I rotated the whole antenna so the white bag opens at the bottom to protect the electronics from rain. I attached a pipe T and 2 short pipe feet at the bottom to hold the antenna's polarization, and I strapped the antenna to a upright post. Ta-da! The EZT antenna is ready for use. I suggest you point your first antenna towards the Earth's equator. Here in the USA, point at perhaps 45 degrees above the southern horizon. So this presentation now uses that experimental antenna to describe ezRA as a convenient way to test data collection hardware. ezRA is still in development, but it seems to work well. The hardware is simple: an old PC with a Smart T SDR to a long TV coax to a Sawbird LNA to the PZT antenna. The Smart T SDR provides 4.5 volts down the coax to power the LNA. On Windows or Linux, follow the included instructions and install the free software of Python and modules and libraries. On a command line, run ezCol, C-O-L, call for data collector. A live graphics screen pops up with 4 plots. At the bottom is a red strip chart of antenna relative signal power of the last 24 hours, with the most recent sample on the right. Above that is a green strip chart of antenna relative signal power of the last 1 hour. And at the top is a blue strip chart of antenna relative signal power of the last 500 samples. Top left is typically a frequency spectrum of the last sample collected. Without hydrogen, here we see a gentle, smooth 3 humps shaped by the electronic circuitry, maybe with a center spike from the SDR. But to improve the data analysis, we can compare those sky samples to other samples that do not show hydrogen. The samples without hydrogen are called reference samples. We expect hydrogen signals near 1420 megahertz, but we do not expect hydrogen signals 3 megahertz higher at 1423 megahertz. ezCol can collect reference samples from non-hydrogen 1423 megahertz by entering a slightly longer command. That command requests alternating antenna sample, then reference sample, then antenna sample, then reference sample, and so on. Here, without hydrogen, we see a reference sample with the gentle, smooth 3 humps. And here, with hydrogen, we see an antenna sample with an extra odd little bump here in the middle. But now that we have reference samples, we can, some live analysis is helpful. I click up here in the top right on RefDiv, and now the frequency spectrum presents the last antenna sample divided by the last reference sample, frequency by frequency. When pointing at the galactic plane, we see a convenient larger bump. I could also click here on RefSub in the top right, and now the frequency spectrum presents the last antenna sample subtracting the last reference sample, frequency by frequency. But I prefer the shape of the earlier RefDiv. I'm about to speak about this new file button way up here in the top right. Here are some data collection file names. ezCol creates human readable .txt names, .txt files. ezCol records time in Universal Coordinated Time, UTC, and ezCol creates a unique data file name upon each program start and with the start of each UTC day. ezCall can run for months. Depending on the number of samples per hour, the data files are 2 megabytes to 25 megabytes each. At my convenience, I milk the collecting PC's data with a USB thumb drive. I choose to start these file names with my ham call sign to signify the latest antenna under test. ezCall then adds the last 2 digits of the year, then the 2-digit month, and then the 2-digit day, followed by the UTC hour that the file was started. With this top file name, I wanted to make changes to the antenna, but I did not want to stop the program and let the SDR cool off. I wanted to keep the SDR warmed up, so I simply clicked that New File button in the top right to start a new file. I can delete this data file later. I made changes to the antenna and then again clicked that New File button. Because the new file was started in the same hour, ezCall created a unique name by adding the next letter from the alphabet, starting with the letter B. Inside that file starts with some header information, followed by many long data lines. The header info includes the telescope's location on Earth and its azimuth and elevation pointing. On this image, I've trimmed the long data lines way over here on the right. Each data line starts with a date time stamp, followed by maybe 256 real numbers. That 256 freak bin quantity can easily be some larger power of 2, like 512 or 1024. ezRA's policy is to provide many switches and adjustments via the command line with useful, simple defaults. Running an ezRA program without arguments usually provides a help screen. ezRA's policy is to create plots, even if they're not always useful for your hardware. The plots can be avoided with the command line or simply be deleted later. Another program is called ezCon, C-O-N, con for condense. It begins the data analysis. It reads those .txt data files. To process just one file, the command might be like this, with Python, the name of the program, and the data file. Or to process all the data files in a directory named data, it might be more like the second line. Now we look at the PZT antenna plots. With the sample number increasing to the right, we see the average power values for the first 50 sample spectra. Their values alternate up and down. ezCon separates those samples into antenna and reference samples. Here we see the stronger antenna samples in blue and the weaker reference samples in red. Blue because the antenna samples come from the blue sky above, and red because reference also starts with the letter R. Here is the full 24-hour day of those samples. The value of the blue antenna samples drift a lot, but it's nice to see the red reference samples generally follow along with the same fluctuations. Those fluctuations are often caused by temperature variation. Here in Colorado, USA, the UTC day starts at 6 p.m. local time. The night slowly cools the air and the electronics work better and provide more amplification and increase the signal strength. At 1200 UTC in the middle is 6 a.m. local time, and the sun begins to warm the day, and the signal strength decreases. We see afternoon clouds come and go. ezCon uses the most recent reference sample to reduce those large signal strength fluctuations. And that day was not unusual. This is a similar plot with several days of data, again with UTC increasing to the right. The night cools the air, the electronics work better, increasing the signal strength. And then at dawn, as sun begins to warm the day and the signal strength decreases, then we see the afternoon clouds come and go. After some signal math, comparing each antenna sample to the most recent reference sample, here is the calculated ANT-RB signal. The first sample time is 00 UTC on the left, and the bottom line says the last sample time is 2359 UTC. Each sample frequency spectrum is one vertical line. This is much like a waterfall plot, but perhaps falling from the right. I see a straight line horizontally across the plot at Doppler 0. ezCon can remove that interference. But I also see a faint wiggling snake across that horizontal center. After trimming the high and low frequencies that are no longer needed, that faint wiggling snake across the horizontal center gets brighter. ezCon suggests how to hide that pesky straight line at Doppler 0. On the command line, I follow its suggestion, and now that plot looks better. The galactic hydrogen signal appears as a snake wiggling once each 24 hours. That wiggle is due to the Earth's rotation on its axis once a day, and the Earth's revolution around the sun once a year, and the sun's motion among its local neighborhood of stars. To properly compare data from different times, we should remove that wiggle. ezCon calculates the VLSR for each sample and applies it to remove that wiggle. VLSR is short for receding velocity of the local standard of rest, which is based on the sun's local neighborhood of stars. Each sample's VLSR value is applied to its vertical line sample in the waterfall plot, and the galactic hydrogen snake is now straighter, less curvy. On this plot, on each vertical line sample, there is a green dot which marks the sample's maximum value. The brightest maximum is then marked with a yellow dot. It's nice to see the maximum dots mostly mark the galactic hydrogen signal that we want to study. Here's the same plot, but now with almost 3 days of data. It has a different shape because it comes from a different antenna elevation above that south horizon. Again, nice to see the strongest values represent the galactic hydrogen. ezCon calculates several signals shown here together. Here at the bottom, this blue galactic latitude trace sometimes show the antenna was pointing above the galactic plane and sometimes was pointing below the galactic plane. When the antenna was pointing at the galactic plane, ezCon marks the galactic crossings with a thin black vertical line. That is where the hydrogen is. The signals above sometimes show a bump in signal on those galactic crossings. For this data, the best galactic bumps seem to be on this bottom trace in violet, right on the vertical lines. Another program is called ezSky. It can plot those 3 days of signal strength averaged onto the radio sky. I plotted that violet signal here in green. The signal strength is shown with vertical offset. The two bumps seem to align with the galactic plane. On this right ascension, and then vertical declination radio sky plot. But I collected day-long drift scan data with the antenna pointing at several different elevations above that south horizon. That translates to several different declinations on the radio sky. ezSky can plot all those signals using vertical offset. Again, the bumps seem to align with the galactic plane on this Radix plot. ezSky can also plot the sky locations of the local maximums and where they fit on the radio sky. The local maximums of those bumps are shown here in green dots, which seem to align with the galactic plane shown here with red dots. Far from the galactic center, these signals on the right were pretty weak, so they did not align as well. Maybe more days of drift scans would average and reduce their random signal noise. That same data can be plotted in color, with bright yellow representing strong signals. But what about all these blank spots between the lines? ezSky can also predict the color of these blank spots. ezSky can interpolate this data with color to paint the radio sky. We can see the galactic plane appears in brighter colors. The same drift scan data can be plotted on galactic coordinates. These drift scans trace complex curves across the galactic sky. And again, the power values can be interpolated with color. And it is nice to see that along these thin black traces, where the data is, it seems to be the brightest along the galactic plane, here along the center. The custom ovals like this in white can mark areas of no data. This white part of the sky is not visible to the telescope. The Earth was in the way. But wait, there's more. Remember all those drift scans across the galactic sky? We can study just the data points near the galactic plane. Perhaps just those points which are within plus or minus 5 degrees latitude of the galactic plane. We find there are many galactic longitudes represented to the left and right, many dots. Here at galactic longitude 118, EasyCon can collect the data and present an averaged frequency spectrum. Another program called ezGal, GAL for galaxy, it can calculate the longitude's velocity spectrum. This is the power received at various receding speeds along that longitude's line of sight. Note that this spectrum has a large peak near zero velocity, and then a smaller peak at a negative velocity, and then a sharp drop-off. ezGal plots this velocity versus galactic longitude plot. Here are all the velocity spectra sorted like books on a shelf, with galactic longitude increasing to the left and velocity increasing up. In here, in a thin vertical line for that vertical spectrum of galactic longitude 118, we can see that there is a large peak near zero velocity, and then a smaller peak at a negative velocity, followed by a sharp drop-off. So that's where it lives. We can barely see a brighter triangle up here near the middle, and strings of beads hanging down here on the left. The professionals make similar plots. Here is their brighter triangle up here in the middle. It's caused by the intergalactic arms, those which are closer to the galactic center than the sun. And here are their strings of beads hanging down on the left. They are caused by the outer galactic arms, which are farther from the galactic center than the sun. With all that information, ezGal can calculate the distances from the sun to the hydrogen clouds. It can then plot those clouds along the galactic longitude angle. ezGal can then interpolate that position data. Even with this minimal antenna, we can start to see brighter galactic arms here. And then over here as well. I'm thinking that's pretty good for a $20 antenna and free software. But wait, there's more. ezRA can do more for folks with more advanced antennas that have motors that can track an object across the sky. That LTO-15 antenna was programmed to collect 15 minutes of data for each 1 degree galactic longitude. ezCon and ezGal plotted this position data and also the interpolated position data. And with more data, galactic arms are clearer. And way over here. With the famous NASA artwork as a guide, the arms can be labeled. But wait, there's more. This plot shows the arms as flat, as if seen from high above. What about the three-dimensional location of hydrogen in the arms? What about the hydrogen in and out of the screen? Another program called ezGlon, this one. Another program called ezGlon for galactic longitude, GLON. It can plot the data along the galactic longitude like this yellow line at 85 degrees. First, data must be collected along that galactic longitude from points along here in green, which is the same as these points along here. And with the galactic plane horizontally now along the middle, with the sun in yellow, ezGlon can point the position data above the galactic plane and below the galactic plane. We can see that data more clearly if we magnify the galactic latitude angles by a factor of 5. and then interpolate the data. Here we see a cross section of the horizontal galactic plane showing 3 galactic arms. Here's one, 2 in red, and a third one in red. Interestingly, the arms are not in that galactic plane, but instead bend upwards a little bit towards the edge. The galactic plane may not be flat. It may be warped. So please give ezRA a try and perhaps help to improve it. If you already have data, ezRA may already include a data converter program for you to use. Or come talk to me. Wow. Okay, thanks for your patience. After all that, Jay, do we have time for questions?
Yes, we do have time for questions. So this is actually followed by an open mic session. So we're not going to rush to close this discussion if people do have questions or comments. Well, you must have answered everybody's questions. Anybody here? Why don't you come on up to the mic? And we have one question from Green Bank.
I love good Python, and I'm looking forward to stealing lots of stuff.
Well, good. The Python's in there. I'm not sure it's good, but it's my effort anyway. I think it's kind of messy inside and needs some cleanup, but I'm just so eager to keep it pushing along.
Okay, who else? Bruce.
Yes, your simple antenna that's put together there. I wonder what kind of beam width you have from that, and any antenna pattern shape or anything run on that? Thank you.
I tried to do a drift scan of the sun to try to get the beam width, and I ran into temperature problems confusing the data and stuff. But I think it looks like about 30 degrees beam width. I used Rich's formula yesterday, and going backwards, that's about a half-meter dish. So this is a pretty small, minimal antenna, but I'm hoping it's even cheaper than a dish you might buy or try to build, and maybe a little simpler to understand in the beginning. I will be posting eventually on ezRA more details about how to build one yourself kind of concept.